So, Marco, can you please start?
Para la lucecita sí se ve.
El del medio.
Ah, sí, sí, sí.
Ya estamos. Ready? Okay, guys, we can begin now with the fight between the two companies. We continue with our second talk. This one is actually the only one. Is the only one talk on physics. So thank you, Professor Abril, because she's contributing to the topic on physics. After the talk, remember we have the workshop on the glucose monitoring, and it's going to be here and here. And after the workshop, we will have the STEM ball, the finals. So stay for the STEM ball, and then we will have the 12% monitor. Okay. Brenda is going to do the introduction.
Welcome, everyone. Today we have Dr. Suarez with us. Dr. Abril Suarez is a physicist specializing in cosmology and theoretical physics, with research focused on dark matter, dark energy, and structure formation in the universe. She earned her PhD in physics from the Centro de Investigación y de Estudios Avanzados del IPN and completed postdoctoral research at the Université Paul Sabatier in France. Dr. Suarez Ramirez is currently a professor and researcher at Arkansas State University, Campus Querétaro. Her work has been published in leading international journals in cosmology and astrophysics, and she has been recognized as a member of Mexico's National System of Researchers. Please give a big round of applause to Dr. Suarez.
So hi everyone. Good afternoon. So I want to start by saying this time I chose to give a talk on something that is not astrophysics and cosmology, everyone, okay? Because most of the time, usually most of the students already know what I'm going to talk about. So I decided to talk about something different, which I want to clarify that I'm not an expert on, okay? But I think I know enough in order to explain at least the idea of how this works. And this is a subject in optics, yes? Why do I think I have some knowledge on this topic? Because I want to say that this was my project when I was in my major. So I graduated with this project when I was a student. So, and actually when I prepared the talk, I realized that I understand more now than then. Okay, so let's see. So what are we going to talk about today? It's, I called my talk Play with Light, the case of optical tweezers. So I will show you how we can use light, everybody, in order to manipulate things. And the idea I want to give you is, you've seen Star Trek, right? Or you've seen Avengers, and you see how they fly in their spaceship and how they trap things with light in outer space. Do you agree with that, everybody? Yes, so this is more or less the idea. You are in your spaceship, and you can trap things and manipulate things with a laser. Yes, that's the idea of optical tweezers. Okay, so the outline of the talk, I will talk about the general problem. What are optical tweezers? I will give you a background. I will talk about momentum of light. I will talk also about something called radiation pressure. After that, I will tell you how optical tweezers work. The setup, so the laser setup. I will talk about the forces that act on optical tweezers. And finally, in my conclusions, I will just talk about applications, okay, why this is important. Okay, so the timeline of how is it that we know or it became, so optical tweezers came to be, everybody. So the first idea, although he didn't really know what he was talking about, was Johannes Kepler, okay? What is the idea of Kepler? Kepler is usually famous because he proposed the laws in which planets move around the sun, okay, which are Kepler's laws. But so he knew very well how astronomical objects can move, okay? So the idea of Kepler had once was that, okay, he saw, because he had a telescope, that comets going around the sun, everybody, if you see this little thing here, it's called the tail of the comet, okay? But somehow he figured out, and he observed, that the tail of the comet always, when it was around the orbit, around the sun, the tail of the comet was always pointing away from the sun, okay? Always. And you can observe that, and you can always see that when a comet is going around the sun, the comet, at the tail of the comet is always pointing the other way. So Kepler asked himself, why is this happening? And without knowing, he proposed, okay, maybe the sun has a certain effect on the matter of the tail of the comet. So somehow, the light of the sun is doing something to the dust that is around the comet, and that's why the tail is going the other way. Yes? That's the only thing he proposed. He didn't know what he was talking about, but he gave like an explanation, a hypothesis of what might be happening there. Yes? So that was the first idea. Maybe the sun, the light from the sun is affecting the tail of the comet. Then afterwards, in 1873, Maxwell came into play, and we know that we have Maxwell's equations that can describe light, everybody. Why can Maxwell's equations describe light? Because light can be described as an electromagnetic wave, okay? And this is the main idea in this kind of things. Light can be described as a wave, okay, everybody? How do you describe that wave? That wave is made up of electric and magnetic fields, okay? And that was the idea of Maxwell. Then after Maxwell, in 1960, it was a scientist called Timothy something, I don't remember his last name, but it was in Bell's laboratories in the US that made the first laser, everybody. So he was able to eject light from a device, and then from that light, so he was the first that made the laser, but then after you had the laser, the question became, what can I do with that? Okay, why do I want to work with that? And one of the ideas that came out is in 1970, this guy, together with his team, also at Bell Labs in the US, they actually found theoretically, so first in the equations, that light can actually have two forces applied on matter, which is one is called the gradient light. We'll talk about that one. And the other one is called scattering force. Okay, so one is gradient force and the other one is called the scattering force. And this guy found with the maths that light can bring those two forces to an object, a gradient force and a scattering force. After that, this was in the 1960s, like 10 years before 1970. And in the late 1970s, he actually found the first application of what those forces that light gave into biological systems. So Arthur Ashkin actually saw that you can manipulate biological systems by using light, using that gradient force and using that scattering force. And due to that, in 1918, he and his team received the Nobel Prize. Okay, so what was the big idea of this? We can use light to actually manipulate things, and this is why they are called optical tweezers, because you agree that with tweezers you can get something and you can manipulate it. Yes, so but actually optical tweezers are much better because you're not touching the system. Okay, so they are like more, they are more pure. If you want this, is a more pure way to manipulate whatever you want to manipulate. Yes, everybody. Okay, so in summary, we have Johannes Kepler, the tail of the comets, saying maybe the sun is doing something to the tail, so it's always pushing the other way. Then you have Maxwell saying that light has an intrinsic electromagnetic nature. So light is made up of electric and magnetic fields. What is the use of this after the invention of laser? And then Arthur Ashkin in 2018 received a Nobel Prize because he said that optical tweezers, so lasers, can be used in their applications to biological systems. Yes, everyone? Okay. So, okay. So, here comes the nice thing. So the first thing that you have to keep in mind, everybody, is that light has momentum. Okay? What is momentum in physics, everybody? Momentum in physics is the ability of an object to move another object. Okay? So light has momentum. What is the momentum of light? The momentum of light will always be proportional to its energy, that is its magnitude, how much the value is. Yes, everybody? And it will always go in the direction of the propagation. Okay, so For the people that have taken physics, you can say, oh my God, but how can light have momentum? If you know that momentum is equal to mass times velocity, and in physics, we know that light has no mass. So if there is no mass, that term should be zero. So that means that momentum should be zero. So that means that light should have no ability to move other objects. Do you agree with that, everybody? Okay, so this is the thing where it becomes weird. Okay, so the momentum should be zero. The momentum should be zero. So the light has the ability to push things, to move things. I would say no, because right now, do you agree that you are getting light from the lamps and the sun, everybody? And you're not feeling that you are pushing yourself. Yes? So that doesn't mean necessarily that light doesn't have momentum. Probably the momentum is very, very small, okay? Or you need a really big source to feel its momentum. And another thing, this equation here that you know in classical physics, everybody, it's only valid whenever this mass is really big and whenever this velocity is really small compared to the speed of light. That equation that you have there is only an approximation. If you take quantum physics into account, and if you take special relativity into account, everybody, you arrive to this equation. And this equation is the equation that describes the momentum of an object if it moves at a velocity close to the speed of light, if it has mass, okay? Not just with masses equal to zero. Clear on this, everybody? So this is the most general equation that you can have, which describes momentum in terms of mass and things that can move close to the speed of light. If your mass is zero, it doesn't matter, everybody, because you agree that you still keep this term. Yes? And if you still keep this term, do you agree that your P is your momentum? So you can solve for P, and you see that your momentum, although you don't have mass, will always be proportional to your energy. Yes? And this is the nice thing. Although light doesn't have a mass, it does have energy because it's a wave, everybody. And the energy of waves always comes from its frequency and its wavelength. Yes? So if you have a laser, do you agree that you have a wavelength because it's light? So if you have a laser, do you agree that you have frequency because it's light? So if you have frequency and if you have frequency and if you have a wavelength, you have energy, and if you have energy, you have momentum. Yes, everybody? So yes, and this guy, which is known, he's Richard Feynman, one of the most famous physicists, particle physicists, asked this question. So why does it bother you that light has no momentum if it has no mass? That doesn't necessarily mean that it doesn't have momentum. Maybe it doesn't have mass, but the momentum can come from the energy. Yes, everybody? Okay, so again, this is just an approximation. If you take math seriously, this is the one you get to. Yes, everybody? Okay, so, okay, so if mass has momentum, everybody, in physics 1, you see that the force is defined as the change in momentum with respect to time. Yes, everybody? So if you have momentum, you can have change in momentum. And if you have change in momentum, you can have a force. Yes? And do you agree that from chemistry or biology or whatever, pressure is defined as force over unit of area. So if you have a force, do you agree that you have pressure? So that means that light can give you pressure, everybody. And if you have pressure, that means that light can push things. So that means that you can, I don't know, if I want to obtain an object here and maintain it here, do you agree that I can push it? So having some pressure, I'll keep it there. So that's exactly what light can do. Yes, everybody? Yes? Okay. So, and this kind of pressure coming from light is called radiation pressure. Okay. So we will see in a minute how this works. Okay, so this is just like for you to know that light has momentum. Okay, and the momentum comes from the energy. Why does it come from your energy? Because your energy has frequency and it has a wavelength. Yes, everybody? So the setup of optical tweezers, everybody. So the easiest idea of the setup, you have a laser, which gives you light, and you have something called the microscope objective, which is the one that focuses the light to the object you want to track. Okay, actually, of the whole setup of optical tweezers, this is the most expensive piece. Okay, apart from the laser. Yes, everybody. So all the lenses, that is the most expensive piece. So the setup, you have a highly focused microscope objective, primary, which is the primary optical component located closest to the object because you want to focus that light to the object, responsible for gathering light, providing magnification, and determining the resolution of the image. Another thing that you can use in optical tweezers, everybody, how you manipulate your objects depends on the kind of laser that you use, okay? And in the case, in the one that I use, is a laser that has something called the Gaussian beam. And what is the Gaussian beam of the laser? A Gaussian beam of a laser is a beam in which its intensity is the strongest in the center. Okay, so at the center of the laser, you have the strongest intensity. Why do you want to get the strongest intensity? So we already know pressure is force over area. Yes, everybody? But do you know that force, we said that it was the changing momentum with respect to time. Yes? In physics, we say that the changing, but do you know that in the case of light, the changing momentum comes from the energy. Yes, everybody? So in physics, we say that the change in energy with respect to time is the intensity. So how much pressure you inject to the object you want to trap depends on the intensity of the laser. Yes, everybody? And why do we use a Gaussian beam? Because a Gaussian beam is the one that has the most intensity in the center. Yes, everybody? So if you want to trap something, this is my beam, and the most intense part is exactly in the center, so that means that my particle will get trapped in the center. Yes, everybody? Okay, so this is a profile of a Gaussian beam. This is another kind of beam, which is called the vessel beam. So you can also have this one. But in this case, when we use this one, we actually trapped things in the different rings of the laser. So that was nice because you have several intensities here. So actually, you can trap different things in the different levels of your laser. Yes. And I wanted to show you this one. So this is a vessel beam, and this is a Gaussian beam. Questions, anybody? No? So, okay. There are several things that are important in order for you to trap things, everybody. Also, it depends on the size of the things you want to trap. And this is very, very important. In the case of the project I did in my major, it was the easiest one. I was just a major student. And this is called classical optics. When do you use classical optics, everybody? Whenever the object you want to trap is much bigger than the beam of your laser, okay? So if the object you want to trap is bigger than the beam, in that case, you use classical optics, everybody. And what is classical optics? Just the laws of refraction and reflection in optics. Yes, everybody? Something is reflected when the beam comes in and then it bounces back. And something is refracted when the beam comes in and then it goes to the medium and changes its direction. That's classical optics. That's the only thing I use. If the object you want to trap is much smaller than the beam, everybody, in that case, you have to use quantum mechanics. So I didn't know quantum mechanics by then, so I didn't use that one. Yes, everybody? So, yes, so interaction of light with the object of interest. Light will be bent according to the laws of reflection and refraction. Any change in the direction of light will result in the change in its momentum, so we'll have a force. So I will explain that in a minute. Okay, so how does this work, everyone? Okay, if you remember the first slide I showed you, okay, we say that the momentum of light depends on its energy, and it goes in the direction of propagation. Yes, everybody? So here it goes. In optical tweezers, you have two forces acting on the object. One is called the scattering force, and the other one is called the gradient force. The scattering force comes from the interaction of the light with the object. So imagine this is the light of your laser, everybody, this one, okay? So it's coming in, and this is the particles you want to trap, yes? So do you agree that as soon as it comes into the object, its direction changes because it's interacting with it, yes? So if the momentum depends on the direction, do you read that as soon as it changes the direction, its momentum changes also? Yes? So that means that you have a force. So here you have a force because the light is changing in the direction as soon as it interacts with the object. So what I say here, so imagine you have your laser here and it's reflected to the left. So then your particle will feel a push to the left. Yes, everybody? But because of laws of conservation of physics, everybody, if you have a change in momentum in one side, because of third law, whatever change in momentum you have, you should have one in the opposite side so everything is conserved. So this bending or this force is because of the bending of the object inside the object. Do you agree with that? Who is my opposite force? That one is called my gradient force, and that one comes from my laser, everybody. If the light is pushing the object to the left, but my laser is very, very focused and it has a really big gradient in the center, that particle will feel also something in pushing it to the gradient of the center of my laser. So that means that the one that is pushing it to the center will contrast the one that is pushing it out. Yes, everybody? So at the end, all of the forces that are acting on my particle will cancel out and it will just stay like it's at rest. Do you understand? And this is why it's nice to have a Gaussian beam, because if you have the same amount of light coming in at all points, everybody, so imagine this is my light in. So here refracted, this is my change in momentum, but so this one is taking my particle outside. Do you agree with that, everybody? Or this one is taking my particle to the left. But then my third law says, okay, this force wants to take my particle going this way. But then I have an opposite force that is keeping it this way, in the opposite direction, yes? So if I have the same amount of rays coming at every single point in the center of my particle, all the forces will add up, and at the end, they will just cancel, and it's like my particle is at rest. Yes, everybody? Okay, so the total forces experienced by the object consists of a scattering force, which comes from the refraction, and the gradient force, which comes from the laser. Scattering force appears when the light beam is scattered by the surface of the object. The gradient force from third law and conservation of momentum, the gradient force is the restoring force that pulls the object into the center of the beam. So once again, this is my beam. Okay, here is my light coming in, everybody. As soon as it interacts, the light will try to keep pushing my particle this way. Because of this intensity, this force will try to push my particle to the center. So these two will cancel out and my particle will still like it's at rest in the middle of my laser. Yes, everyone? Okay. So, if the lens used to focus the beam is perfectly in the middle of the laser, so that's why you want, so this is why you want the objective, because you want to focus exactly in the middle. Okay, so you want to keep it there. So this is why you buy this little thing here. Okay, if the lens used to focus a beam is perfectly in the middle of a laser, there is an equal light going through both sides, and the net force will be zero. So you will just keep it still in the middle of your beam. Yes, everybody? So what I see here is, imagine here, the laser is coming, okay? The light will try to scatter it away from it, but the center of the beam has the more intense, so you have the more pressure. So this is the one that is contrasting going this way, so we'll keep it this way. And this is what I mean here. Let's see. Oh, no, wait. So I want, why is it not moving? Okay, this should be, there it is. So there it is. Yes, everyone? Okay, so there you have it. Okay, questions? No? Okay, so applications of this. So more or less the theory of how this works, everybody? Yes? If not, you can ask me questions at the end. But okay, let's see the applications. So this is what I did in my major as a project, everybody. So it was a final project of major in physics at the Universidad Autónoma Metropolitana in Iztapalapa. And this is a photo I took when I was in my major. This was our laser setup, and that back then it was a huge table. and you had a huge laser, and you had a lot of lenses, and the objective lens at the end, because you wanted to try to focus to the objective. Yes, everybody? And then we had a screen, and we could watch whatever we tracked. So we tracked objects much bigger than the wavelength of the light beam. So that means we use classical optics. Yes, everybody? So just refraction and reflection. First, which is the first kind of particles that we tried to track? It was polystyrene balls. Okay, they are synthetic balls. Most common material, which is the most common material you start with in order to track these kind of things. The size typically range from 50 nanometers to 10 micrometers, chosen because of the high refractive index. So if you have a high refractive index, what does that mean, everybody? That means that it will refract a lot when it goes into the direction. And if it refracts a lot, do you agree that you will also have a force that it goes opposite that is really big? Yes, everybody? So the more refraction you have, the more chance you have to pull the object to the laser, to the center of the laser. So that is why you want to high refractive index. So we trap this in water. So we put a little balls in water, everybody. And we use a high refractive index to allow for strong stable trapping. And after we were able to trap polystyrene balls, we decided to trap blood cells, because at the end, what my professor wanted to do at the end is a project to see if you could use these things to measure certain biological properties. Yes, so we use red blood cells. Like any major student, I didn't know how to work with that. So I will tell you several things I did when I was a student that are funny right now. It wasn't that funny back then. So yes, so first it was great. So my job as a student, everybody, first, my professor told me, okay, this is my project. I want to do this. We have the tools to create optical tweezers in the university. I don't know how to do that. You do that, align the laser and trap something, okay? So my job was to put the lenses in several arranges to see which one was the best. And at the end, I was able to trap polystyrene balls. And after we got so we got really good at trapping polystyrene balls, we decided to see if we could trap blood cells, in particular red blood cells. Yes, everybody? Okay. What is the difference when you work with these kind of things with biological systems? Polystyrene balls are synthetic balls, everybody. Okay, so it doesn't really matter the energy of your laser. I mean, we will see in a minute what kind of laser. It doesn't really matter because it's synthetic, so nothing will happen to it. So you can just trap it and keep it. You have to be careful with biological systems because if your laser is too energetic, everybody, you burn them. Okay, and then that's not good if you want to do certain studies. Okay, so I will tell you about that in a minute. Which is the laser I used when I was in my major? It was an argon laser. That was in 2005, so a long time ago, everybody, which is 488 nanometers or 514 nanometers in wavelength. And after that, I just seen the pictures of my professor and how the project is. So before giving the talk, they have a really nice laser now. It's very small, so compared to mine that I use like this one. So now they have a really small table and a really small laser. And they have a different laser now, which is an ND-JAC, so which is made of neodymium, titano, neutron, aluminum, and garnet. What is the difference between this laser and this laser? Of what I read, everybody, is that this laser, the temperature of the beam is much smaller than the temperature of this one. So if you want to trap biological systems, this one is much nicer than this one, because this one will not burn your biological system as easy as the other one. Yes, everybody? And this is one of the things so first, how did I trap my red blood cells when I was a student, everybody? So I didn't know what equipment to use. So after I trapped the polystyrene, I got the, what I did, I had a needle with me. So I pinched my finger and I put my blood in the samples, and then I focused my blood in the samples. And one of the things, so you have to be very careful with the energy of your laser. So one of the things I noticed is when I put my blood in the sample, so in the objective, everybody, my laser beam was too intense. And as soon as I put the blood, you can see in the screen, if they got trapped somehow, they get absorbed because they were, so, I mean, the water in the blood cells, I don't know, it was just absorbed, and you can just see them like crunching like this as soon as they got trapped. Yes, everybody? So that's not good because you cannot maintain them, and then you trap them and then they just squeeze. And that's what happened with my red blood cells. Yes, everybody? So, okay, so once you know which kind of, so I wanted to show you this video because it's my professor, okay, Dr. Hernandez, he's the one that directed my project. He's explaining a little bit about how, what is the aim of optical tweezers. Yes, everybody? So what I want you to see is, everybody here speaks Spanish or somebody doesn't? If not, I will explain at the end, okay? So I just want you to see. Is there a
Click on
sound?
this image.
There's sound in
I
there?
think so, yes.
Yes. Okay. I don't think so.
El doctor José Luis Hernández Pozos y el maestro en ciencias Nahum Méndez Alba, del Departamento de Física de la Universidad Autónoma Metropolitana, Unidad Iztapalapa, diseñaron un sistema de pinzas ópticas dirigido a la captura y manipulación de glóbulos rojos, lo que ayudará a determinar el daño causado por la diabetes.
Lo que podemos observar con estas pinzas ópticas es la capacidad de estirar que tiene un glóbulo rojo. Los glóbulos rojos deben circular por capilares y estos capilares normalmente pueden tener una micra de diámetro, mientras que el glóbulo rojo en su estado normal tiene alrededor de 8 o 10 micras. Entonces, para poder caber en estos pequeños capilares tienen que deformarse mucho. Uno de los problemas con la gente que tiene diabetes avanzada es que esta capacidad de formación decrece muchísimo, a tal punto que muchas veces impide que los glóbulos rojos pasen por estos capilares, lo cual trae como consecuencia pues, que ya no tenga una oxigenación adecuada en las extremidades sobre todo. Con toda certeza definir, decir, este es diabético, este no, creo que ya lo podemos decir con bastante precisión, y luego los que son diabéticos, la idea es tratar de decir qué tan dañadas están tus células.
En entrevista, el doctor Hernández Pozos indicó que el científico Arthur Ashkin fue pionero en la investigación de los sistemas de trampa láser. También explicó el funcionamiento del sistema de captura.
Las pinzas ópticas fundamentalmente es una herramienta que consiste de una fuente de luz, en particular un láser, y la envía a través de una lente que enfoca esta luz. Quiere decir que la voy a enviar a través de lente.
Es que moviste la parte, se movió.
Sí. A ver si puedo los rollos. Aquí. Es que no está conectado esto.
No, porque estaba es que nada más tiene.
No, tiene. Ok, bueno, sí, no.
Ok. Ok, bueno, espérame. Que no se ve ahora. Ok.
Las partículas, en este caso glóbulos rojos, se sienten atraídas hacia la zona donde hay más intensidad y se quedan ahí atrapadas. Por ejemplo, aquí nada más ahorita tenemos información mecánica, es decir, estiramos estas glóbulos rojos, estas células, y medimos su elasticidad.
El maestro en ciencias Nahum Méndez tiene 6 años trabajando en la investigación y fue quien armó y calibró el sistema que permite atrapar por medio de un haz de láser partículas del tamaño de unas cuantas micras.
Lo que hacemos es que el haz se divida en una proporción 50-50. Dejamos que el haz principal vaya hacia la pinza y el otro haz lo recombinamos inmediatamente después por medio de esta óptica. Finalmente entran los dos colineales y llegan hasta la parte de la pinza, que es justamente en esta celda.
El doctor José Luis Hernández señaló los objetivos del sistema de pinzas de manipulación óptica para colaborar en el área médica. Al respecto, añadió:
Es que este sistema ahorita no está capacitado para obtener información química. Podría uno tener la información mecánica, simplemente de estirar las células, al mismo tiempo obtener la información química para que sean al menos dos técnicas que corroboren la información una con otra. Se puede tener glóbulos rojos o a lo mejor otro tipo de células o a lo mejor partículas de algún material que le interese estudiar, sostenidas quietas en un cierto volumen, atrapadas por estos láseres. Esta tecnología yo creo que tiene mucho potencial para aplicaciones biológicas y en general para manipulación de microobjetos. Apenas estamos entrando a explorar las potencialidades de este tipo de sistemas. Yo creo que hay muchísimo que desarrollar.
Universidad Autónoma Metropolitana.
Okay, so, okay. Okay, there it is. Okay, so, conclusions, everybody. Optical tweezers are highly accurate tools widely used in science, as you have seen, okay? The basic principle of optical tweezers is momentum change or momentum transfer, if you want to call it like that, associated with the bending of light, and then you have radiation pressure. What's happening? Okay, optical tweezers are very expensive and custom built instruments, so they are not easy to obtain. Okay, the precise set of the optical trap is accomplished with lenses, mirrors, and electro-optical devices that are controlled via computers. The lasers can't be controlled to move. So once you trap your object, everybody, the lasers via computers can be controlled to move, either move, stretch, or do other things to the object. This might allow scientists, for example, to measure minute forces of the order of piconewtons. Optical tweezers have proven useful in many areas of physics, chemistry, and mainly biology. So as I told you, my aim was just to build a set of trap things, and that's it, everybody. But for example, in Cambridge, this is a red blood cell already, everybody. And what they are doing is they're not just trapping, but they're actually now deformating the cells to see. So you have a laser. So you have a laser here. You have a laser here. They have trapped the red blood cell from both sides. And what they are doing is moving the lasers in order to see if they can stretch or compress the red blood cells. So that's, for example, that. Okay. Yes, everybody? So those are one of the things you can do. Okay. Applications may include confinement, organization, tracking of movement, measure of small forces, and altering the structure of objects. Objects like viruses, bacteria, living cells, organelles, and DNA have already been trapped with using optical tweezers, everybody. They are also used in synthetic biology to construct tissue-like networks or artificial cells, to fuse synthetic membranes, to initiate biochemical and chemical reactions, and it's also done to research on chromosome and structure dynamics. Yes, so I think in this, what this photo shows you, everybody, is I think what they did here is that they have a cell, I don't know which kind of cell, and they put, so they trapped it with the laser, and they put some sort of substance inside the cell, and they manipulate the substance inside to see how it deforms the cell. Okay, so you have two optical tweezers there. So one to trap the cell, another one to inject whatever they are injecting, and then move that substance inside the cell, and all of this is done. And you can see that as they move this one, the cell is deformating. Yes, everybody? Okay. And another application in quantum physics, everybody, quantum computers, okay? Small motors in computers. So here they created a motor. I don't know what this is, but this is a particle. And this is like a little motor that you can find in quantum computers. And so you have, and all of that, all of those three objects are trapped with optical tweezers. Yes, and you are manipulating them with optical tweezers.
What is the orange?
The
It's
orange.
like attracting the light?
No, I think probably that's just a sensor to measure something.
Oh.
You don't see really the beam of light there. And this is just for you to see that these are rubidium atoms trapped individually, everybody, with optical tweezers. So you can trap them and you can manipulate them and arrange them in whatever way you want. Yes, in that case, the object you are trapping is much smaller than the beam of light that you are using. So for that this particular kind of problems, for sure you have to use quantum electrodynamics in the equations to be able to model those kind of objects, which is not like the spheres or the blood cells, which are much bigger than the wavelength of myelins. Yes, everybody? So, okay, in short, these are very complicated instruments that require a working knowledge of microscopy, optics, and laser techniques. It is a non-invasive scientific tool that uses light from a highly focused laser beam to trap, hold, and manipulate microscopic and submicroscopic objects in a manner similar to tweezers. And that is the idea that I wanted to talk to you about today. Okay, so thank you, everybody.
Okay, guys, any questions? Remember, questions in English or Spanish, or however you feel more comfortable. Question?
Since, since these aren't actually physical tweezers, there is no actual risk that you will, for instance, accidentally cut or accidentally squish a particle too much.
So in this case, the cut and the squeezing don't exist because you are not so you're not cutting like a scissor blade per se, okay? And in the case of a squeezing, that is why you have to be careful with the wavelength and the intensity of your. So you have, all of these you have to measure before you actually prop whatever. And intensity is so the intensity will tell you how much pressure you want to inject in the object. Okay, so if you already know the wavelength of your laser and the size of the object, there is no problem with the pressure. What is more concerning about optical tweezers in the case of biological systems is the temperature of your laser. So if you have too much temperature in order to manipulate biological objects, then you will burn things. I mean, for sure. So in this case, you have, if there are synthetic things, you don't have to worry about that either. Yes, so that's the nice thing about this. Yes.
Another question? ¿Otra pregunta?
No?
As a user, you trap your blood cells, but when you have very small medium, so you mentioned water, but I don't think something the laser was like pointing upwards, downwards, and
So the laser is focusing from the front. So you have your microscope objective, and you have your sample here, and then your particles are in here, right? So the intensity of the laser comes here. Your microscope objective focuses the laser, and that is what it keeps it exactly trapped in your objective. Yes, Ellie? Yes.
So, what is like the lower limit? Like, what would be currently like the smallest thing that you could manipulate?
So right now I have no idea. I mean, but I mean, if they already manipulated individual atoms,
Okay.
I think that's
Very small.
exactly. So I don't know.
Well, that's interesting.
As small as I can, yes. So I mean, they are doing this for quantum computing specifically.
Yes.
Yes.
And another question. So when you said what you did with your blood sample, do you have any guess as to why the cells were like?
So I don't know. I mean, what I suppose back then, but I don't know too much biology, is I suppose water cells have, I mean, red blood cells have water, a certain amount
Yeah.
of water. So as soon as, because in that case, my laser was too intense.
Right.
So the heat, as soon as they felt the heat, they just like evaporated or
So
something
it
like that.
kind of sounds like it might be something in the solution is breaking apart, Like not in the cells themselves, but some molecule is breaking apart into the high energy. And then you have an osmotic phenomenon where all the water.
So probably because I mean the only thing I did was use so they gave me a solution. I don't even remember what that was. So they gave me a solution in order to maintain my red blood cells.
Right.
But as I told you, the only thing I did, I mean, I didn't really have anything to manipulate so I just
Right.
pinched myself, put it in there, and that was it. So I don't know if something in there got contaminated or I have no idea. But now they do things very differently, and now they don't see this anymore because they know how to manipulate, and because the laser they are using right now, at least at one, is very different from the one I used back then, because the intensity of this one is less hot, so you don't have too much heat in the new one. Yes,
Right.
yes.
When you trap the cells, does it affect like the internal systems of the cell, like the dynamics that of the system?
I suppose so. I don't know. You have to ask them. I suppose so. I mean, if they get crunched or absorbed, I don't know how to call it. I suppose yes. Yes. But I mean, this is why I say at the end is a non-invasive tool, because it's not the same picking you with tweezers, actual physical tweezers in which you invade much more than if you just touch with light. So, but I suppose it does. Yes.
What would it take, or is it possible to spread something much bigger?
Not in this case, because then the momentum of light is not enough. Okay, unless you have something that is really intense. So it's like the example. So now we know why Kepler said that the tail of the comets were pointing. So in that case, because the sun is huge, indeed the sun is creating some radiation pressure in the dust of the tail of the comet. So in that case, you are seeing the effect of the radiation pressure, but it's because the sun is really big. Okay, so I mean, I don't know, we will need a huge source of light in order to trap one of us, for example. I mean, we don't feel, and I mean huge, because although we have the sun, and this is what I mentioned at the beginning, we don't feel the effects of, I don't feel the air of the sun pushing me. So the momentum that the sun is transferring to me is really small, although the sun is huge. Yes?
I have a question. If you go back to the image where the cell is elongated and shrink.
The red blood cell,
It's just by light, right?
Yes.
The cell is deformed because of light, but how is that possible? How the light is like sticky to elongate the cell?
So it's not that it's sticky.
I mean, just like you put it.
So you have
what's forcing the cell to deform? That is my.
exactly. So because it's trapped right now, so you trapped it in this side, and you trapped it in this side. So you have two lasers in this case.
Yes, but what is in physics the light doing to the membrane to pull it in one direction, because there is light that is going to.
So I mean, the way you manipulate the laser, it's via computer. So once you trapped it, and how you trap it is because of the scattering force and the gradient force. So once you trapped it and all the forces are equal to 0, it's like this one is still here, and this one is still here. So you have still from both sides because all your forces are 0. So you trap this side and you trap this side. Once it's trapped, you can move it. Via computer, so you can move your laser. So here you are moving your laser. What you are moving is your laser, but it's trapped already. So you are moving your laser this way, and that is why because the red blood cell is already trapped. So you're moving your laser this way, and then the trap is being stretched that way.
Yes, but my question is like how the laser is moving the cell.
No, the cell is moving with the laser.
It's like a differences in charges, or what is the principle of moving, elongating the cell?
I don't understand. So the principle is this one. I mean, you already trapped your cell.
Mm-hmm.
So you have So yeah, so you have your forces acting on your cell, so you have your light coming in, right? And the light, the momentum of light will try to deviate the cell to another direction, okay? But because of the gradient of the beam, you have a gradient force, and that gradient will try to turn it back into the highest intensity of your laser. So while the photons are trying to push it this way, the gradient of your laser is trying to put it back way, this way. Okay, so the more refraction, the more gradient you will have. So that means that you have this one from the light, but because of conservation forces, this one will try to pull it backwards. And then these two will cancel out, so you keep it fixed in the middle. Yes? Yes.
Another question?
Yes.
The idea of light path momentum is basically the same mechanism that makes solar sails possible, right? It's something very
No, so solar cells capture energy.
solar sail.
I-
You
No, what's that?
you have a satellite and you have like a giant, basically a giant mirror, and you reflect light from the sun and move the satellite.
But yeah, but that you're not catching the satellite with the sun. So you are getting, so exactly, so you are getting, but you're, in that case, you are getting energy into the mirror and then reflecting to get a signal back. So that is like signal reading instead of catching the satellite and moving the satellite with the light. So it's not the same principle.
But it's still the momentum of light.
No, in that case, it's the energy. Oh, so it's energy related to momentum, but you're not using the momentum to have a force. So you're just accumulating energy in your lenses. Yes? 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 More questions? Any? No?
Okay, thank you. Dr.
Yes?
Felicia.
Okay, so thank you, everybody.
Okay, we continue at 2 with the workshop. It's going to be here, remember, the workshop with glucose monitoring. So if you want to stay or you want to come back.